All right, the last unit we're going to talk about is chapter 15 in our text, and it's on oscillations. This is really important. This represents so many things in nature, and let me describe it real quickly, and then I'll go over how it describes so many different things in nature. Well, let's make a simple coordinate system. This is an x-axis, and let's put a particle in the center, some mass. If this particle travels to some plus x and then back through, so it loops back around, comes back through our x equals 0, comes out to some plus or minus x, and then returns back to where it started. That's an oscillation. Think about if some systems we've had before, if we put a mass on a spring and we displaced it. So we pulled this out to maybe here and let it go. If this is frictionless, and if it's not frictionless, it's still going to represent an oscillation. It's going to oscillate back and forth until forever if there's no friction and we don't lose any energy in the spring. But if we lose energy in the spring and there's friction, it'll start slowly dampening down. And I'll talk about dampening too. But what we're looking at is something that's going back and forth and back and forth and back and forth. And we need to think about that as sinusoidal motions. All right, something that oscillates goes to some max and then down to some minimum and back to where it started. I also would like you to start thinking about all of these topics as going in a circle. If we start at x is equal to 0, the x-axis, and make it all the way around one time, we called that 2 pi radians, right? The time it took to go around is equal to the period. Well, we're going to use all those terms to describe oscillations. So let's start with simple harmonic motion, and then we'll get a little bit harder. We'll often see this as SHN, simple harmonic motion. First, let's define a couple things. The period is the time for it to go all the way around the circle, or all the way to do one full cycle of a sinusoidal function, or something like a particle oscillating between plus and minus x. It's the time for it to go all the way to plus, all the way to minus, and all the way back. So it has to make one full cycle. And we call that full cycle the period, or the time it takes to do one full cycle. We can then define the frequency as 1 over the period, and the frequency is in hertz, and it's how many things something does per second, how many oscillations per second. So period is how many seconds for one oscillation. Frequency is the inverse, or how many oscillations per second. Okay, now if we can describe the motion as going between some maximum and then back through its equilibrium, x is equal to 0, because right, this can be x, this can be y, this can be z, this can be some angle theta. It can be anything regarding displacement and or position. Anything that goes to some maximum, back through its equilibrium point, down to some minimum, back to its equilibrium point, can be represented with a sinusoidal function. And in this case, we're going to choose a cosine function. So we'll say that on this, let me redraw it real quick. we have some particle m going between plus x and minus x. We can figure out its position anytime t by saying where it was to start times the cosine of omega t plus b. And I'll define those in just a second. This is referred to as the amplitude. So this would be this distance right here, x n. That is, if I plotted the sinusoidal function of the cosine, this function right here, x of t versus t, that's going to look like cosine starts at 1 and then goes something like that. And then that would be one period, and then continues through. The amplitude, the amplitude refers to the maximum height right here. This is equal to minus the amplitude. So it oscillates back and forth between what we call that amplitude. The omega here is why we're going to talk about things in a circular fashion, because this is what we call the angular frequency. How fast is it sweeping through something, right? The change in angle with respect to time. This is time itself, so that would be our variable. And this would be over here on the x-axis. And the last one is what we call the phase shift. Now, what's a phase shift? Well, if I took this exact graph and instead of starting right here, I start right here and just shift everything over, this is shifted by some speed. That is a phase shift. That's simple. You'll see this in the motion we're talking about in this class. We'll see it in electronics and circuits and stuff. Let's get back into this angular frequency a little bit more, though. Possibly a confusing topic. Term. Angular frequency. All right, the quantity omega is angular frequency of the motion, and it's related to the frequency f and the period t, right? Those are both related to each other, dependent on each other. So by definition, some of the motion we're talking about, something has to go back. So start here, go out to some point, go to its opposite or negative point, and then come all the way back. So full circle, right? Like this. For that to happen, the position must return to it has to return to the same position at some t plus t, so at some later time. We can go ahead and, in this case, say phi is equal to 0, and returning to the same position, that's the most important part. This particle returns to the same position. We'll take that position formula I just gave you, and then set it equal to it at some later time, some t plus t. Since it repeats itself, the phase increases by 2 pi. By 2 pi radians. If I don't say radians with it, that always associate that quantity with it. If I say 2 pi, we're probably talking about radians. Okay, so if it goes through 2 pi, it means it has gone full circle, or if you remember on our it takes 2 pi to go one full cycle on a sinusoidal function. Then we can cancel, we get omega t is equal to omega t plus some 2 pi. Oh, sorry. It's gone 2 pi radians. Distributing this out ends up canceling one out, and we just get omega times the period is equal to 2 pi. And this gives us a definition for our angular frequency as 2 pi over the period. And if the period is equal, or the frequency is equal to 1 over the period, we can also say this is equal to 2 pi times the frequency. That's a useful definition, and the unit would be radians per second. Okay, what does it look like if something's frequency increases or decreases? Well, if that was its initial frequency, let's say its frequency increased, that means its period gets smaller, and the same thing would have to fit inside a smaller area. The period increased, that means the frequency got so yeah, the period for one full cycle means the graph would look something like that. That's pretty bad. I'm going to try to get those to scale. They need to all have the same amplitudes, what I'm trying to get. If I extended our period out to something like this, our initial period is like this. The frequency went down and the period went up. And that's supposed to come down. If I reduce the period to some t3, the frequency actually becomes larger. It's going to have to fit one waveform in that same amount of space, or the smaller amount of space. Like that. All right, that relates omega, our angular frequency, our frequency, and our period. All right, what if I want to know the velocity of something with simple harmonic motion? Well, we take the time derivative, right? That's what we've always done before. The velocity is equal to the time derivative of x with respect to time. We had a formula for x, so we can just take that time derivative. We have some amplitude times the cosine of omega t plus b, a phase shift. And that gives us a function for our velocity at any time t we can calculate. That it is equal to minus omega, and bring the omega out, times the amplitude, and then the derivative gives us the minus sine, and we keep the argument, or the phase. This whole argument right here is called the phase. So omega t plus b. And there's a function for our velocity. And we can take this one step further and get our acceleration. The acceleration would be the time derivative again, and we pull omega out one more time to get omega squared times the amplitude, and we'd end up with the cosine function again, omega t plus So if you have something's function of position, you can easily get to its velocity or acceleration by the derivatives. All right. If we want the acceleration, we just want the amplitude sometimes. What if we just want the amplitude of the acceleration in this thing right here? Well, we can find that by just calculating at any time t minus omega squared x of t. That will give you its derivative equation. Okay, now let's look at that example of the mass on a spring. This is what we will call the force law for simple harmonic motion. Okay, so if we can say the second law, force is equal to mass times acceleration, we can substitute in here omega squared minus omega squared x, because we just calculated that for our acceleration right there. And if you remember, the force on a spring from Hooke's law was minus kx, meaning it was acting in the opposite direction of its displacement. We can combine these two and actually get what's actually very useful. If we know k and we know the mass, we can figure out the oscillation frequency right away. So if you know the spring constant and you know the mass, it doesn't matter how much you displace it. And you'll see that same thing for when I'll look at a pendulum. Something goes back and forth. The only thing it matters is the only thing that controls the period is the length. In this case, it doesn't matter about the displacement. It just matters about that constant k and the mass. Two separate little things. I'll show you the pendulum in a moment. What we can do is say that solving this, omega is angular frequency, is the square root of k over m. And that can be also turned into using our formula for the period is 2 pi omega. Or sorry, 2 pi times the frequency. We can write this as 2 pi times the square root of m over k. And that would give us the period if we knew the mass. This would give us angular frequency if we knew the mass. We'd have to know the mass and the spring constant. Sorry. All right. I'm going to breeze through the energy due to oscillations. There's a whole science on this. You might take a class called vibrations if you're an engineer, mechanical engineer. What the whole section in the book boils down to is if we have something oscillating with some like a mass on a spring, the energy just ends up being potential plus the kinetic, just like before, and it's just equal to 1/2 mx, or 1/2 kx squared. So they do a whole derivation where these sine squared plus cosine squared is equal to 1 to reduce it, and it all reduces down to this. The energy of the system is just really related to that oscillation of how far out is it and what's the k value. Now let's talk about pendulums real quick. I'll leave the derivation up to you. It's in the book. I know we're running out of time, but we'll also look at this as circular motion. And I hope you see the connection between circular motion, something going around one time in a certain amount of time, one revolution, something that goes through one cycle, right? Literally think unit circle to a sinusoidal function, right? They got that relationship. Okay, a simple pendulum is when we have some length of string, L, attached to a small mass, or any mass, and it pivots about some point. In this case, we'll attach it to a ceiling. Now, this is going to take some path, and it's going to keep going back and forth and back and forth and back and forth until, if it's in a vacuum, it'd go forever, as long as it wasn't losing energy to maybe the string or the bearing or the pivot point up here. Or if it was swinging through air, it's going to lose some of its energy to drag, or the frictional force of fluid. But it's going to go back and forth, right? Regardless. And that represents simple harmonic motion. We're going to look at what's called the simple pendulum. And then I'll talk about what the physical pendulum is and what the difference is. If we look at the forces on here, we have the force of gravity, mg. We would then want to break it into components along the path and in this direction, along the length of the string, or in the r direction, right? The unit r direction. The perpendicular component here is what we're interested in, fg sine theta. We should also note that this length of arc can be related to the length of the string times this angle theta. All right. If we say that there's some torque, right? This is a force right here acting at some distance L, and we're going to call that a restoring torque. As it swings out, this is going to restore its energy as it swings back through, right? As it swings out, it comes to a stop. Then it comes to a maximum speed right through the center, and then slows down, comes to a stop, goes through a maximum in the other direction, and so on. And once again, a full cycle would be if we started over here, for it to go all the way through and come back, right? A pendulum we have to displace, so we wouldn't start it at x equals 0. It wouldn't do anything, right? It would just sit there and hang there. So if we displace it some theta, it's gonna make it through some other negative theta like such, and oscillate back and forth. We'll see that theta needs to be small though, and that will come from our approximation we're about to make. It's a useful approximation, that's why I'm deriving this for you. If we say that the torques equal to this Fg sine theta, and it's acting in a direction that would cause it to be a negative, right? This would cause a rotation in the clockwise direction, so I'm going to throw a negative sign on there. It's acting at a distance L. We remember Newton's second law for rotations. It said that the sum of the torques is equal to I alpha, we only have one torque acting in the direction of motion. We can say that negative L F sine theta is equal to I alpha. And we can solve this for alpha. The alpha is equal to mgl over I. And this is all times theta, or sorry, times the sine of theta. Now, this is where we have to use the small angle approximation for sine, where in radians, very important, in radians only, the sine of theta is very close to theta. Type it in your calculator. Type sine of 0.01. I bet it comes out to about 0.01. Meaning we can just throw theta here instead of sine theta. Like, right? And the book says it's a neat trick. This has the same form for simple harmonic motion, and we can immediately identify the pendulum's angular frequency. The angular frequency would be equal to the square root of the contents in front of the displacement of this stuff right here. This is the displacement. If we take the stuff in front of it and take the square root of it, that'll give us the frequency for our system. So how fast it's oscillating, how many radians per second. Then we can say that the period is equal to 2 pi times the frequency, or the square root of I over L. If we have what's called a simple pendulum and just a mass on a very, very small mass, like a particle, on the end of a string of length L, and we'd use the moment of inertia as mr squared, this period L over G. This is for pendulums and small particles, small amplitudes, sorry. So what is this small angle approximation good for? It's about 10 degrees in degrees, but really 5 degrees is where it's actually pretty accurate. Depends on what book you look at. I've seen some books that say it's good up to 15 degrees, but I would never do that. 10 degrees max. 5 degrees, you're definitely safe. But you should know that we're always doing the approximation in radians. And if you're a physicist, you will see this again, I promise. Okay, now I just wanted to talk real quick. What if this thing was actually real, right? Nothing is just a particle on a string. The string even has mass. Everything is a blob of mass like this, right? This is pulled out some angle. Well, what's going to change is that there's a crazy mass distribution, and we'll call this in this case, for small amplitudes for a physical pendulum, we would need to know the shape, and based on the shape, we can get the period at this moment of inertia over